Is already live streaming?
Yes.
Yeah. Mohan, can you check? I am just talking over phone.
Sorry,
Can
Lakshmi?
you check whether it is live?
Okay, I will check. Just a minute.
Yeah, he told it is live.
Message had appeared on the screen.
Oh, 1 second, man. Wait, I will confirm it.
Now is streaming live.
Yes, it is live. It is live.
Yeah, it is live. It is already live in YouTube.
Thank you. You make me host, okay? Yeah, very good day to all the panelists as well as the participants, and welcome to the lecture series of online open classroom online lecture series in atmospheric and climate sciences organized by SAMA and SRM-IST. So we have completed 4 orientation lectures. Now we are entering the first submodule of the atmospheric physics module, that is an atmospheric thermodynamics. So without taking time, so I invite Professor Someshwar Das to welcome the panelists as well as the participants of today's session. Over to you, sir.
Okay, thank you, Dr. Lakshmi Kumar. ABM Professor Ajit Tyagi, President of SAMA. Dr. Kyaw Mo Wu, the Director General of Meteorology, Myanmar. Professor Bhaskar Rao, Honorary Professor, Andhra University, Waltair. He is also the member of the advisory committee of the lecture series. And today's speaker, he's also my teacher, by the way. Members of the organizing committee, Dr. Madan Sikhdel, Dr. Rohini, Dr. Lakshmi, Dr. Mohan, Dr. Akhilesh. Participants, ladies and gentlemen, a very warm welcome to all of you on behalf of the South Asian Meteorological Association and the SRM Institute of Science and Technology, Chennai. I'm glad to inform you that the number of registration of our lecture series has exceeded 2,000 from more than 40 countries. This is the 5th lecture today, and Professor Bhaskar Rao is the first speaker of the module on atmospheric physics, sub-module on atmospheric thermodynamics. As you know, the entire lecture series is designed for capacity building of people in the field of atmospheric, weather and climate sciences. We have distinguished panel of very senior professors and scientists from reputed institutions of this region who are experts in the field. They will deliver lectures on the fundamentals of this subject. The lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of weather and climate sciences for research and operations. As you know, we have already completed 4 orientation lectures by now. The remaining 12 lectures of this series will be on different aspects of atmospheric physics, including atmospheric thermodynamics, which will be covered by Professor Bhaskar Rao starting from today, then atmospheric radiation and cloud physics, which will be covered subsequently by other experts. This lecture series, as you know, will continue for 4 months till April 2023. As already announced, certificates will be given to the participants who have registered for the course and will complete the entire course with at least 75% attendance and successful performance in an evaluation test at the end of the course. The lecture series are live streamed on the YouTube channel of SAMA. They will also be available afterwards on the YouTube for those who could not attend the lecture on live. We shall try to have more interactions between the speaker and the participants in this lecture series. Please write your questions in the chat box. Our moderators will pick up the questions at the end of the lecture and they will be answered by the speaker. So enjoy the lectures and wish you all the best. Over to you, Dr. Lakshmi.
Thank you very much, Professor Someshwar Das, for welcoming the panelists and participants, and also briefing about the course. So now I request Professor Ajit Tyagi, sir, President, South Asian Meteorological Association, to speak a few words about the relevance of today's topic. Over to you, sir. Tyagi, sir.
Thank you, Lakshmi and Somesh. It's really a great honor to start the real series on the open layer lectures today. And there wouldn't have been a better speaker than Professor Bhaskar Rao, who has been guru as not only of Somesh, but many luminaries who have reached the pinnacle in India and internationally. He is a guru in a true Indian tradition that he's selflessly working even at this stage of his post-retirement, totally dedicated in promoting atmospheric weather and climate sciences. Thank you so much, Professor Bhaskar Rao, for guiding us, SAMA, and spreading this knowledge to a wider community of young researchers and students. We are very much encouraged by your support to us, and I'm sure this series will immensely benefit from this. I'm also thankful to our advisory panel member and Director General of Myanmar Meteorological Department, who has agreed to give his comments for today's lectures. We have been getting very good support from Myanmar, thanks to Dr. Wu. And all this wouldn't have been possible without, I think, active participation of the ECT members, support from the SRM IST, Lakshmi, and all other colleagues who have been actively participating and supporting this lecture series. As Somesh has already outlined the entire scope of these lectures, and also the interactions which will be open in the question answer form. Its availability even after the session is over. You can go through the recordings if those who have missed or those who want to again refer. So it's a great opportunity for all of you, and also those who, because of time zones or other reasons, could not attend. These resources will be available and will be shared with them. It is no doubt an overwhelming response, and we are touched by your participation and look forward. And I'm sure these lectures will benefit, enhance your knowledge. Though you see, thermodynamics looks like very simple, pressure, temperature, humidity, density, but this forms the basis of entire weather and climate systems. Simple, but very important. And as I told you, there wouldn't have been a better teacher than Professor Bhaskar Rao to cover these topics to the basics with clarity. So enjoy these lectures, make best use of it, ask questions. I am sure you will immensely benefit. Thank you.
Thank you, Tyagi, sir. So now I request Dr. Wu, Director General for Meteorology and Hydrology Division, Myanmar, to speak about a few words of this lecture series and today's lecture. Over to you, sir. Dr. Wu.
Thank you. Excellency, distinguished expert, participants, ladies and gentlemen. Good afternoon. It is a great honor and privilege for me to deliver a brief remark at the auspicious occasion of the Open Classroom online lecture series in Atmospheric and Climate Science, jointly organized by South Asian Meteorological Association and SRM Institute of Science and Technology. I do expect indeed thanks to organizer for providing necessary arrangement and honorary expert Professor UC Mohandi, IID, Upanava, Dr. M. Moa, Veteran, DGN, IMD, Professor SKTS, IID Daily, Dr. Rednan, NERN, ISRO, Professor Bhaskar Rao, Honorary Professor, Andhra University, Dr. B. Marco Pathe, IMD Pone, and Professor P. Pradit Kumar, SPBU Pone. As all of you know, many countries in South Asia have experienced climate change and natural disasters such as cyclone, flood flash, earthquake, landslide, heat wave, cold wave, drought, and abnormal weather which has substantially increased. In order to reduce the loss of life and property due to these natural disaster and climate change effects, we require to preventive measure and effective disaster management, preparedness and effective accurate RD1A system. Everybody know human resources is very important to develop each organization. I believe today training is supporting to develop your knowledge in atmosphere and climate science. This subject is very important in climate monitoring and forecasting system. Today's training module is the structure of atmosphere, vertically distribution of temperature, presented by Professor Rao D.V. Bhaskar Rao. Ladies and gentlemen, we do hope that in this training, the participant can more understand the atmosphere and climate science by using technology such as climate change and preparedness and planning of disaster, focusing on early warning or disaster event. I also believe that the participant will improve and understand the analysis and utilization of atmosphere and climate change in the training. I would like to encourage all participants to take part actively in this training. I am confident that the outcome of the training will be meaningful and productive with the added participation for future development in effective RD1A system, climate change activity, and disaster management activity. In conclusion, I would like to take this opportunity to express my sincerely thanks to Professor Ajit, Professor Bhaskar Rao, Honorary Professor from Andhra University, experts from all organizations for your contribution to knowledge sharing and for providing necessary support to make this very important training. I wish this training more fruitful and constructive and great success. Thank you.
Thank you, Dr. Wu, for providing your valuable remarks. So now we will be starting the session today. So I request Dr. Rohini to introduce today's speaker. Over to you, Rohini.
Dr. Lakshmi, would you like to share this screen? Thank you. So it's a great honor to introduce Professor D.V. Bhaskar Rao, who is Honorary Professor presently at Andhra University. So Professor Bhaskar Rao has served Andhra University in several capacities as Professor, Chairman, Head of the department from 1976 to 2008. He initiated teaching and research programs in atmospheric modeling and numerical weather prediction and mentored 16 doctoral students and several MTech and MSc students at Andhra University. He is known for his contributions to atmospheric modeling, tropical cyclone prediction, and numerical weather prediction. Professor Bhaskar Rao worked as visiting professor at Jackson State University, MS, USA, from 2009 to 2013. He worked as distinguished professor and director of the Center for Atmospheric Science at KL University, AP, during 2014 to 17, where he initiated research programs in atmospheric modeling and weather prediction. Dr. Bhaskar Rao published two books. One is Numerical Weather Prediction, published by the IMS, and the other is Mesoscale Modeling of Atmospheric Processes in India, which was published by the Department of Science and Technology, that is DST, Government of India, and made chapter contributions in 5 books, and he has almost published more than 80 research papers. Dr. Bhaskar Rao had several collaborations with scientists in Japan, Italy, Germany, Portugal, and USA through several scientific visits. He had been recipient of many research recognitions, some of which I would like to name: Dr. B.N. Desai Award by Indian Meteorological Society, Fellow of AP Academy of Sciences, Fellow of Indian Geophysical Union, Best Academician, and Best Researcher Awards by Andhra University. He has served on many scientific and selection committees of the DST, SERB, IMD, IITM, and several universities in India. He had been reviewer for several scientific journals that include Nature Scientific Reports, Journal of Geophysical Research, GRL, Meteorology and Atmospheric Physics, Atmospheric Research, Natural Hazards, Marine Geodesy, Geophysica International, International Journal for Environmental Research, and Public Health, Journal of Earth System Science, MOSM, Journal of Applied Hydrology, and many more. Professor Bhaskar Rao is widely known amongst the meteorological community in India for his teaching and research contributions. Welcome, sir. Over to you.
Thank you, Dr. Rohini, for introducing Bhaskar Rao, sir. Now I request Professor D.V. Bhaskar Rao to present his lecture. Over to you, sir.
Thank you, Dr. Lakshmi Kumar. At the outset, at the beginning of these 4 lecture series that have been allotted to me on the atmospheric thermodynamics starting from today, before I start my lectures, I wish to thank Professor Ajit Tyagi, President SAMA, Professor Someshwar Das, Secretary SAMA, and the advisory panel for asking me to do this job. I feel very happy that the opportunity is given to me to teach these 4 lectures. I am very much thankful to the SAMA for giving me this opportunity. I am also thankful to Dr. Lakshmi Kumar and Dr. Akhilesh and Dr. Rohini for helping me with this presentation today. As per the discussions in SAMA, I have been given even the topics of the 4 lectures broadly. What are the topics that are to be covered under these 4 lectures? I have been given some particular kind of a guideline has been provided to me. I will probably adapt to those things as much as possible. But I also wish to say that I have prepared these presentations to be as simple as possible, so that whoever is listening or trying to follow should not have any problem, because for 2 reasons. One is I do not know the background of all the participants, because I'm told that as many as 2,000 people have registered for this course, and across 41 countries or so, because I have no idea about their background. So keeping that in view, keeping that in mind, I have prepared these presentations. So kindly bear with me if if they're too simple for many of the participants. I will be very happy if there will be a feedback at the end of this first lecture. If the things are too fundamental, maybe I should not spend more time on these fundamentals, but I should spend more on the other things. That I will try to cope up with them in the next 3 lectures. But the first lecture, I will make it as simple as possible. These are the main reasons why probably I thought that basically I am a teacher. I do not want any kind of an ambiguity in the presentation. So I did my best. So bear with me, and you can give me your feedback at the end. So with this small comments, I will start my first lecture. The first lecture is on the structure of the atmosphere and vertical distribution of the temperature. So the topics I would cover is composition of the atmosphere, vertical structure of the atmosphere, lapse rates, that is dry adiabatic, moist adiabatic. Then we go to some definitions of potential temperature, virtual temperature. These are the 5 subtopics that have been given to me. I will cover all these 5. Apart from this, I will try to give as much information as possible to follow these things. So we know atmosphere, Earth's atmosphere, and where we live in, because of the presence of the atmosphere, we are all the living is happening on this planet. So atmosphere is generally known as a layer of a gas or a mixture of gases that envelop any planet, because Earth is not the only planet which is having an atmosphere, but there are other planets also in the solar system which have the atmospheres. But each atmosphere of each planet has its own distinctions. And any atmosphere that would surround the planet like Earth, it is it clings to the Earth planet because of the force of the gravity. All of us know, because the planets and any body with a mass will have a force of gravity, and because of the gravitational force, the atmosphere is held to the Earth, as of the other planets also. And coming to the atmosphere of the Earth, it provides us the air to breathe that sustains life on this planet. And the atmosphere is, you will see that the beauty of this nature, how the atmosphere helps us to sustain life on this planet. It provides the air to breathe. It also protects us from some bad radiations, harmful radiations coming from sun and other sources. And also it keeps our planet warm enough for us to be as comfortable as possible. That's very important. It keeps our planet warm enough. And the Earth's atmosphere extends up to about 500 kilometers approximately, of which 99% lies within the lowest part of the atmosphere, lowest 30 kilometers or so from the Earth's surface. So though the Earth's atmosphere extends for as much as up to 500, and most of it is within the lowest strata of about 30 kilometers from the Earth's surface. And coming to the composition, as I said, the atmosphere is a mixture of gases. It essentially contains nitrogen, which is 78% of the total volume, and oxygen 21%. These two gases constitute as much as 90% of the total volume of the gas. There are several other gases which actually makes the weather people interest to weather people. I don't know how to do this. So about the remaining 1% include carbon dioxide. You will see the importance later as the subject develops. Carbon dioxide, which is only about 350, 380 parts per million. Ozone is only 0.04 parts per million. Chlorofluorocarbons has 0.0002 parts per million. And importantly, there is a variable called water vapor. It is not a constant approximately, but it is a continuously, the presence of the water vapor varies in the atmosphere. It varies it is about 1% at sea level, and it decreases with altitude, but the percentage may vary and change up to about 4%. So most importantly, the 1% of the gases, which we talk about, carbon dioxide, ozone, water vapor, they play a very important role. So this small table gives you information about the various gases. On the left side, we see there are permanent gases like nitrogen, oxygen, argon, neon, helium, hydrogen, xenon, etc. And on the right side, we see there are variable gases like water vapor, carbon dioxide, methane, nitrous oxide, ozone, dust particles, chlorofluorocarbons, etc. And we have given the volume of these things also. On this side, in the water vapor, you see that there is a variable, like it varies from 0 to 4%. The other ones are more or less, they vary, but they don't vary as much. They don't vary with time as much as this, but the water vapor varies continuously in space and time. Nitrogen, as we know, it is a colorless, waterless, non-toxic gas. Nitrogen undergoes transformation due to the interacting process between the atmosphere, land, and water, and the living things as we interfere. Nitrogen is needed to make the chlorophyll in the plants as a part of the photosynthesis process. importantly, nitrogen is an important fertilizer because very much used in the agricultural practices, but it also contributes to increase of the emissions of a greenhouse gas, and it is considered to be when it enters the atmosphere, it is 300 times more potent than carbon dioxide. So as the subject develops in the present context of the global warming climate, some of this information may become useful. Oxygen constitute 21%. We know it is important for respiration. It is also important and necessary for burning anything. And oxygen is helpful in creating or the formation of ozone in the stratosphere, and the presence of ozone in the stratosphere actually helps us, protects us from the harmful ultraviolet radiation coming to the Earth's surface. Carbon dioxide, though it constitutes only about 0.03% of the atmosphere, it is an important greenhouse gas. But at this point, I can say what a greenhouse gas means. That means this particular gas follows a greenhouse effect, because in the greenhouse, as we see many places, through a glass, the radiation can pass through, but it cannot go back. That means it is a gas that is transparent to the incoming solar radiation. The greenhouse gas means these gases, most of them in the atmosphere, as you see, as you go to the radiation part later, you will realize that most of the atmosphere is transparent to the incoming solar radiation, but it is opaque to the outgoing terrestrial radiation. That means radiation emitted from the Earth's surface. It is opaque. That means it has the effect of absorbing the outgoing radiation from the Earth. That's called terrestrial radiation. So that helps actually to keep the atmosphere warmer than otherwise. So greenhouse gas means, just keep it in your mind that it does not absorb the incoming solar radiation. It is transparent to that, but it is an effective absorbent for the outgoing long wave radiation from the Earth. That's very important. So CO2 in the present context of global warming also plays a very important, because we note that the carbon dioxide, the amount of carbon dioxide has increased by 35% since 1750. This is presently of great concern, as it effectively contributes to the observed current global warming trend. Water vapor is the gaseous phase. We know that water exists in the atmosphere in all its three phases, like vapor, liquid, and ice. And water vapor is the gaseous phase of the water. And water vapor is also a greenhouse gas. I will talk about it. Under typical conditions, that means under certain conditions, water vapor is produced by evaporation. That means when liquid water or ice is subjected to evaporation, the liquid water molecules would be converted to water vapor. So that is the process of evaporation. And also that the water vapor will be converted to liquid water through a process called condensation. So the change of phase of water vapor takes place in the atmosphere from all interlinked, from vapor to liquid and ice, liquid to vapor and ice, etc. So water vapor, though present, it is a very important part that plays an important role in the weather and climate. That's what we have to keep in mind. Water vapor is lighter or less denser than the dry air. So we are now talking about the mixture. So dry air means there is no moisture at all, but water vapor separately, it is much less denser than the dry air. The density of the dry air is about 1.27 grams per liter, and the water vapor density is about 0.0048 grams per liter. at the standard temperature and pressure points. So it is very important that you should remember that the water vapor is very less dense, much less denser than the dry air. This has a lot of impact on the entire thermodynamics loops around this. Water vapor is also an important greenhouse gas because it significantly contributes the warming of the Earth's atmosphere. And also the presence of water vapor due to the processes of evaporation and condensation, there is a redistribution of the heat energy at any time when there is a possible phase change. The redistribution of heat energy takes place in the atmosphere. Is a very important thing which you will realize as we go further. It also plays an important role in understanding or in the stability and instability of the atmosphere. Just maybe in the next or the third class, we will see what is the atmospheric stability, what is atmospheric instability, and what is the water vapor role. That's water vapor plays a very important role in determining the stability and instability of the atmosphere. So actually, its lighter nature or the lesser density triggers convection currents that also lead to the formation of the clouds. So water vapor is a very important greenhouse gas in the atmosphere. It's a variable. It is not a constant. So this is one variable which we need to keep in mind. Methane is another important greenhouse gas, and the methane is actually because of the agricultural practices, energy sectors, emission, fossil fuel burnings from the coal, oil, natural gas, biofuels, etc. Many of these processes lead to the release of methane into the atmosphere. And because of this human activity, we realize that the methane concentrations have increased by more than 150%, more than 150% since 1750. You can see that as the industrial era has set in, how the methane concentrations have increased. And though it is in small quantities, it is also an important greenhouse gas. Nitrous oxide is another important greenhouse gas. It is a source from the agriculture, burning of fossil fuels, etc. And since during the last 250 years or so, it increased by more than 20%. You can see methane has increased by 150%, nitrous oxide has increased by 20%. Ozone is another important variable or the gas which is very important for meteorologists. It is mostly found in the stratosphere, lower part of the stratosphere, which is called the ozone layer, that is between 20 to 30 kilometers above the ground surface. You will realize it after we talk about the vertical structure. The ozone layer absorbs the sun's ultraviolet radiation. That means that particular component in the sun's spectrum, there is ultraviolet part of the radiation that is coming in, which is harmful for the human beings living on the earth. And ozone plays a very important role of absorbing this sun's ultraviolet radiation. Thus, it protects the humans or the living beings on the earth from the harmful ultraviolet radiation. It is also found in the troposphere. If it is found very near, it is realized as a pollutant. And in the upper troposphere, it acts as a greenhouse gas. So because it absorbs the outgoing long wave radiation. But otherwise, ozone, its importance lies in the lower stratosphere, where actually it starts absorbing the ultraviolet radiation. Aerosols are the particles released into the atmosphere during the activities, industries, and then many particular kind of the burnings, etc. We release aerosols into the atmosphere. Aerosols severely affect the passage of the solar radiation, scattering, reflection, etc. It also affects the cloud formation because some of the aerosols could be taken as condensation nuclei, which become a source for the cloud formulation. And aerosols are known as particulate matter in the atmosphere as an air pollutant. So some of these aerosols are recognized as particulate matter as an air pollutant, which is not good for the human beings and the living human beings because it adds to the pollution. Chlorofluorocarbons and hydrochlorofluorocarbons are very, very small in the quantity. Why we need to mention is because, as I said, they are fully halogenated hydrocarbon that contains carbon, hydrogen, chlorine, fluorine, etc. And some are they produced as derivatives of methane, ethane, and propane. Some of these things actually cause the presence of the CFCs and HCFCs in the atmosphere. And sometimes when we use the refrigerant sprays, solvents, CFCs also are released. Though they are very, very small in the amount, as I said, about 2 billion, 2 parts in billion or more than, and smaller than that, CFs are very inert. That means they stay in the atmosphere for a very long time without getting destroyed. That's why they slowly, though they originate at the surface, they drift upwards towards the stratosphere, where the CFC molecules are broken up by ultraviolet radiation because of that, and it releases chlorine atoms especially. These CFCs will have their molecules broken through a reaction with ultraviolet radiation, and which will actually, these chlorine atoms will destroy the ozone molecules in the lower stratosphere. Just a few minutes before I said the ozone in the lower stratosphere is very important. It protects the human beings from the ultraviolet radiation, and any destruction of the ozone in the lower stratosphere gives a lot of complication because it enhances the vulnerability of the human beings to the ultraviolet radiation. So, though very, very small in quantity, CFCs and hydrofluorocarbons do contribute to the weather and climate. Why? Because people, maybe many of you are aware, there was a observation of ozone hole in the polar regions, and there was actually a lot of work that has been gone into the formation of the ozone hole, and then now we realize that after many precautions have been taken, the ozone layer started filling up during the last 2-3 years. This this is the information about the composition of the atmosphere. Now I will move to the next part. Before I go into more details of the structure of the atmosphere, I will define something. We use time and again a gas constant represented by capital R. It is the gas constant because there's a proportionate constant of proportionality. In the atmospheric thermodynamics, we use this particular gas constant very much. And before I go to the virtual temperature, potential temperature, I thought that this information is very important. So the gas constant R is defined as the Avogadro constant multiplied by the Boltzmann, because you know Avogadro constant Na and the Boltzmann constant. Avogadro constant relates the matter to the mass to the heat of the one, and the Boltzmann constant relates the kinetic energy to the temperature. So these two things are being used. Avogadro is a very fundamental constant known for everybody in the physics. So R is Na into K, and this particular constant R, molar gas constant is given as 8. When you take these two values for Na and K, you can see what are those values. It is very easy. Avogadro's number, and Avogadro's number is about 6.2 in 10 to the power of 23, like that. So the SI value can be calculated very easily from those two, multiply them. It gives you about 8.31, etc. joules per Kelvin per molecule. The dimensions are m, l to the power of 2, t to the power of -2, k to the power of -1. So this is important. The gas constant, if you want to identify a particular gas, then you have to say this, that particular for the gas, R star by M. R star is this molar gas constant, 8.31, and M is the mass of that particular gas. So accordingly, the gas constant for dry air, RD, is equal to, if you divide 8.3144, etc., with a 287, you will get 0.0289, etc., kilograms per molecule. Similarly, the gas constant for water vapor is, because the mass of water vapor is 0.01, molar mass is 0.0180, etc. So R star by M. So if you divide this 8.3144 with the 0.0180, etc., then you will get RB, that the gas constant for water vapor is equal to 461 joules per degree Kelvin per kilogram. So time and again, we will be using this gas constant for dry air and the water vapor. So I thought it is an information which you should know. Well, we will define some properties of the atmosphere. Maybe many of you are aware. Air density is defined as the number of air molecules per unit volume. And near sea level, its value is about 2.7 in 10 to the power of 19 molecules per cubic centimeter. The density of the dry air, at the sea level is in metric units. Of course, you can see the two units is about 1.225 kilogram per cubic meter. So the density of dry air, because we'll be using these things later, for any kind of a thermodynamic analysis, you should know the molecular mass, you should know the density, you should know the gas constant. All these things will be used to derive many of the atmospheric thermodynamics parameters. Air as we are dealing with, it is easily compressed. That means its density could increase when it is squeezed into a smaller volume. Solids and liquids are not easily compressed, but air is easily compressed. So this particular property of the air, so the density, whatever it has been said, could be changed very easily. So if there is a small volume, if all the particles are being compressed to get into a smaller volume, the density will increase. Similarly, because of the property that at the surface of the earth, near the surface of the earth, the density, the air molecules are the largest in number. So the density is higher near the sea level, and it decreases upward as we go up. So because of more particles would be clinging to the atmosphere due to the force of gravity, and we see that the more number of molecules would stay very near to the Earth's surface, and some of them, and slowly their density decreases upward. Pressure is also something which we know very well. It is defined as the force per unit area, and the pressure is dependent on the magnitude of the force that is applied and the area onto which it is applied. So the greater the force exerted and the smaller the surface area that is exerted, the higher is the pressure. So we know these concepts, but I thought it would help us with the next concepts. Atmospheric pressure results from the Earth's gravitational pull on the overlying air. So because the air is being pulled towards the center of the Earth due to the gravitational force, so we see that the vertical pressure force results because of the Earth's gravitational pull. And the weight of the atmosphere, so the weight of the air as the molecules that stay in that acts as a force on the surface of the Earth. So the amount of the force exerted over a surface area is called the atmospheric pressure. So in the atmosphere, It is the amount of the force exerted over a surface area. So at the sea level, the average air pressure is about 10,1013 hectopascal or millibars that is there. At a later stage, maybe I will show you the units, how that come in. It means that the total weight of all the air above the sea level weighs enough to cause 1013 hectopascals of air pressure. Since the air is like a fluid, the pressure force acts in all directions, not just downward. Because if you take a volume element of air, it will have the pressure acting in all directions. And the pressure force, because of this height, it decreases. So the pressure force decreases with height because as it goes up, the weight of the air column above that is going to be smaller and smaller. So the international system of the units, also called the SI system, is the one currently used in meteorology, is derived from the old metric system. So the unit of pressure is Pascal, what we write it as PA, which is equal to 1 Newton per square meter. And the unit Pascal came into existence only after 1970. And prior to that, the pressure used to be expressed in newtons per square meter. And the dimensions are ml-1, that means mass, length, and time. And here, 1 Pascal is equal to 10 dynes per square centimeter, or that is equal to 0.01 millibar. So it is 1 atmosphere is 1013.25 hectopascals, or 760 millimeters of mercury. That means 1 atmosphere is a unit of measurement equal to the average air pressure at sea level at a temperature of 15 degrees. So we have to see because the pressure and the density would change with the temperature also. So at a standard temperature of 15 degrees at the sea level, the average pressure, the average air pressure is determined as about 1013.25 hectopascal or millibar. So in meteorology, pressure is generally expressed as hectopascal. Previously, it used to be millibar. And if we see this figure, we see that it is the highest, the pressure as well as the pressure Pascal. This is the vertical coordinate for the pressure. This is the vertical coordinate for the density, kilograms per cubic meter. So this thick line is air density, and this line, dashed line, is the atmospheric pressure. You see that both of them decrease very fast, and not linearly, but in a way exponentially. Later you will see how this pressure decreases with height, and is it possible for us to understand how this pressure decreases with height? Is there is a mathematical explanation which we would find, and on what factors the decrease of the pressure and density with height? We will see that also as a part of this course. And the temperature is another parameter which we are going to deal with in the thermodynamics or the basics of the meteorology. It is the degree of heat, hotness, or coldness. Temperature is an intensive property like pressure or density. It is independent of the quantity of the matter, because it's not how many molecules are there that is there, but it is distinct. It is distinctly different because from the mass or volume. It is some properties similar to pressure and density, not as mass or volume. So the pressure, density, and temperature are very important for us because these three are called intensive properties and then subjected to change, and which are also interrelated. The temperature scale, the Fahrenheit, every one of us knows, Celsius, and the Kelvin scale. Actually, Celsius scale has been derived following the freezing and the boiling points of the water, as many of us know. And he took the freezing point of the water, boiling point of the water, and divided the interval into 100 parts. And the centigrade or the Celsius scale came into existence. The Kelvin actually considered the lowest possible temperature at which there will be no energy present, which he called it as zero. That is what actually in the literature it is called absolute zero. That means where no energy could be present in the particle at all. So the Kelvin scale started zero, and that corresponds to minus 273.15 degrees centigrade. And so the Celsius scale is obtained by shifting the Kelvin scale by 273.15 degrees. So just for information, how the Celsius and the Kelvin scales originated. Whereas in the Fahrenheit, all Celsius, Kelvin, Fahrenheit, all three names of three scientists for the information. So Fahrenheit devised the temperature scale. He took a mixture of ice and salt mixture, considered that as 0 degrees, and it selected the values of 32 and 212 that correspond to the freezing and boiling points of water. So he started with a mixture, ice and salt mixture, and then he considered as 0. And in his experiments, he found that his scale, freezing and boiling points have occurred at 32 and 212. And because of the 180 difference between these two, so he made it 180 equal parts. And in this, you can, if you are interested, you can read how he, why did he put 32 degrees and then 212. He considered the human temperature also into consideration, and then started adjusting the scales. Okay. So some conversions I have given. If someone wants to do this, it is very easy. All of them are interrelated. And now we come to the vertical structure of the atmosphere. And vertical structure of the atmosphere, why we should do it? Why we should do it? Because unless you know that there is a variation, that means not only horizontally, because people live on the surface, and it is possible for us to experience the variations in the weather parameters like pressure, temperature, density, all of pressure and temperature and humidity. Most of them we can experience at the surface, but how to know the structure of the atmosphere, that means vertical structure, how these variables behave as we go up from the surface of the earth towards the space. So actually measurements, atmospheric measurements through radiosonde balloons, aircraft, rockets, and now these days satellites have revealed the very useful information that the atmospheric temperature is not uniform. So in the beginning, we might be feeling that it is uniform. And in the beginning, people knew that the temperature probably decreases with altitude because the people living near the sea level, that means with less of the elevation, their temperatures were higher. And if you go to the higher elevations, the temperature decreases, because if you have a mountain very, very nearby and you stay at the base and then you climb up the mountain, then you will see a lot of difference in the temperatures, because that's the one thing which you can feel very easily from your human skin, because it is quite sensitive. So people felt that the temperature may be decreasing with altitude, but the measurements, radiosonde measurements, started as early as 1900s. They have clearly revealed that the temperature rapidly decreased near the Earth's surface. And there have been some variations, at least because the radiosonde measurements were confined to mostly the lower part of the Earth. So they have identified some decrease of the temperature in some layers and some increase of the temperatures in some layers. So near the surface, they found the decrease of the temperature, and about 10 kilometers or so, they found an increase in the temperature. So it is also, they were puzzled in the beginning because there was the decrease in the temperature. Later, the temperature was increasing, but many of the measurements have helped us to understand the vertical structure of the temperature. based on vertical structure based on the temperature. So this is a figure which shows the variation of the temperature. The x-axis is the temperature in degrees centigrade. Y-axis is the altitude in kilometers. You see that at the lowest level, very near the Earth's surface, from 0 to about 10, 12, 14, there is the temperature. The temperature was decreasing. The temperature is decreasing from the surface to about 10 or 12 kilometers or so. And above that, there was a small layer. There was a small layer which is isothermal. Then the temperature increased up to about 50 kilometers. Then there was again an isothermal layer. And again, the temperature decreased up to about 80 kilometers. Then there was a small isothermal layer. And again, the temperature started increasing. So it was not like a constant decrease, constant increase, etc. throughout the atmosphere, but it has some consistent patterns, like at the lowest layer or at the lowest levels. Here it is said, so I will define them. So this lowest layer where the temperature decreases with height is called troposphere, and the layer above which the small layer which separates the troposphere and stratosphere is called tropopause. And from the tropopause, there was a small isothermal layer, and the increase of the temperature takes place till the top of the stratosphere, where we call the partition between the stratosphere and mesosphere as a stratopause. And above the stratopause, there was a small isothermal layer. And again, the temperature decreases in the mesosphere up to, so this decrease is called, this decreased part is taken as mesosphere, and the top of this mesosphere and the partition layer between the mesosphere and the above layer called thermosphere is called a mesopause. So troposphere, stratosphere, mesosphere, thermosphere, exosphere. So the small thin layers of separation between the layers of certain pattern, either decrease or increase, have been named as pause, tropopause, stratopause, mesopause, etc. I will give you some information about these things. So this is the pattern that is observed. Troposphere is the lowermost layer of the atmosphere. It contains almost like 75% of the total mass. All that means all the atmosphere, 75% of the total mass is contained in this particular troposphere. For that reason, and also because all the weather changes, including the formation of clouds, occur only in this layer. The height of the troposphere, though shown as constant in the picture, it varies from latitude. It is more at the equator, less at the poles, and the observations indicate that they are nearly the height of the troposphere is about 18 kilometers near the equator, and at the poles it would be as small as about 8 kilometers. And later you will realize the temperature of the air masses near the equator, near the poles, how they contribute for the thickness also. We will see as we progress in our talk. In the troposphere, there is, we have shown a temperature decrease with height. It is average picture from the observations have shown that the rate of decrease of the temperature with height is about 6 degrees centigrade per kilometer in the troposphere. Here the temperature decreases with height is explained as because the incoming solar radiation, the atmosphere is mostly transparent to the incoming solar radiation. So most of the radiation coming from the sun reaches the Earth's surface and heats it up. So the Earth's surface is warmer because it absorbs, that means it has a lot of the solar radiation directly coming and reaching the surface of the Earth, and the Earth's surface absorbs the incoming solar radiation. And so for that reason, Earth's surface and very near the Earth's surface, the atmosphere is warmer. So the air or the atmosphere above the Earth's surface is heated from the ground below, not from the above, because sun's radiation do not contribute to the heating of the atmosphere directly, but the sun's radiation contributes to heating the ground directly, because the atmosphere is mostly transparent to the incoming solar radiation. The solar radiation reaches the Earth's surface, heats the ground, and when ground warms up, it gives up the heat below, from below to the atmosphere above. So the atmosphere is heated from the warm ground below. That's the reason why the temperature decreases with height. It is also possible, although it is shown that the temperature decreases with height, a shallow inversion layer may also be noticed under typical circumstances where the air temperature increases and with increasing altitude, that may increases with height. These inversion layers sometimes are very important to understand the weather and then forecasting, and the formation of an inversion just above the ground, it happens just above the ground. That means very near the ground, because during long winter nights, there is a lot of cooling near the ground. That means the ground gets cooled much more than the atmosphere, because for the same reason, the ground loses heat much more quickly, and the ground is colder than the atmosphere above, in which case the inversion layer happens. This is a typical atmospheric condition that happens during long winter nights. So atmosphere gets, the earth gets cooled, surface gets cooled, and the atmosphere immediately above is a bit warmer than the ground. So that is a typical inversion that happens in the near the surface. And there are many other possibilities for the inversions to occur, but this is only an example. And this fog which forms, because we know that the winter times, the fog formation is quite natural, and which will persist till the morning, and then enough radiation, the ground should be heated again, the temperature should rise, and slowly the fog will vanish. There is, I said, there is a tropopause. Tropopause is a zone that separates. Tropopause is a zone that separates the troposphere from the stratosphere. It's a small fictitious layer we call, because below that the temperature decreases, and above that there is a small isothermal layer with the temperatures to be about 80 degrees centigrade over the equator and about 45 degrees centigrade over the poles, because I said the temperature decrease average is about 6 degrees centigrade per kilometer, but the height of the troposphere is about 18 kilometers near the equator and 8 kilometers near the poles. That's the reason why the difference between the temperatures near the tropopause over the equator and the poles. So this tropopause acts like a lid. So this particular kind of an isothermal layer acts as a lid. That means whatever the convection currents, rising air, etc., all of them would be subdued as they reach this, because of the isothermal layer. They will not penetrate into the stratosphere, and so all the weather activity would be pertained to below in the troposphere only. So that especially the clouds which originate, and they are typically confined only to the troposphere, that is below the tropopause. Stratosphere is the second layer immediately above the troposphere and extends up to a height of about 15 kilometers as shown. In this layer, temperature increases with altitude because there is a presence of ozone. As I said before, ozone is present in the lower stratosphere and which absorbs ultraviolet radiation. So this particular absorption of the incoming radiation, that particular part of the spectrum, which is called ultraviolet part, which is getting absorbed by ozone. So only some major part of the ultraviolet radiation is absorbed by ozone in the stratosphere. So the stratosphere is, in the stratosphere, temperature increases with height. And and weather, there is no weather phenomena that is observed in the stratosphere. And so that is the reason why many of the airplanes fly in the stratospheric altitudes, because they will have a smooth ride. In the troposphere, there will be a lot of turbulence, vertical variations of the wind. So that's okay. The stratosphere contains very little water vapor, because as we said, water vapor and all the atmospheric mass is confined to the near the surface of the earth, and it decreases as it goes up. So stratosphere contains very, very little water vapor. So clouds do not form here, but exceptionally polar stratospheric clouds sometimes appear in the lower stratosphere near the poles during winter, when the temperatures go below minus 78 degrees centigrade. So this is some special phenomena that is observed in the stratosphere over the polar regions and in the winter hemisphere. And because of the very low temperatures and because of the typical atmospheric wind circulations, these stratospheric clouds may form, not every day or so, but sometimes occasionally. And these atmospheric circulations also lead to holes, because I said, as I said in the beginning, the chlorofluorocarbons, though they are very small, they are very, very inert. That means they will not get destroyed very easily. They will be taken by vertical currents in the troposphere up. They penetrate to the troposphere slowly under some conditions whenever there is a possibility. In the stratosphere, these get circulated all over the globe. Although that means in the world, in the circulations, they will be taken away to the polar regions where the ozone concentration generally observed has led to the presence of the chlorofluorocarbons. As I said, they react with the ultraviolet radiation and then get split up and releases chlorine particles, and these chlorine molecules will actually destroy the ozone through a chemical reaction. So this is a very important region, stratosphere. Mesosphere is one that extends up to a height of about 80 kilometers. And in this layer, the temperature decreases with height again. And because the main reason is that at these altitudes, there is more of radiative cooling by the carbon dioxide that is present at that, and more of the thermal radiation being lost into space upward, and lesser radiative heating. That means that the mass is more, there could be more radiative heating, but because of the lower densities, there is lesser of the radiative heating and more of the radiative cooling. And because of the thermal radiation upward into space, that particular part of the atmosphere, mesosphere, the temperature decreases with height. And the meteorites born in this layer on entering from the outer space, not very much connected, but sometimes only of interest. Next one is thermosphere, and which extends from about 80 to 400 kilometers. It is also called ionosphere, and it is again a region where highest temperatures are found, and there is an increase of the temperature with height in this thermosphere because the ultraviolet radiation is absorbed by the molecules present there, and also because of the very low pressure that inhibits the transfer of energy between particles. But that means whatever the energy that's being absorbed stay with that particular particle, and there is lesser of the movement of the particles because of the very, very low density. And radio waves, we know that transmitted from the earth are reflected back to the earth by this layer, and a lot of information has been ionospheric reflections. Your communication, etc. These people use these layers, and the reflective nature of this layer is being used. And this layer is referred to as ionosphere because it contains electrical charged particles called ions. not much of interest to us. The exosphere is the uppermost layer. Above the thermosphere, it is only a small layer which actually gradually merges with outer space. And now we come to our part. This is actually some vertical structure, composition of the atmosphere, which are necessary for us to go forward. And from these two, we have identified from the composition of the atmosphere what are the important gases that are there apart from the nitrogen and oxygen, though they constitute 99%, the smaller volumes that are contained as by carbon dioxide, water vapor, most importantly, and some other gases like nitrous oxide, methane, etc. But carbon dioxide and water vapor are the most important things which we need to bother about. So carbon dioxide, we just leave it because it will come when you start working on the atmospheric radiation. But water vapor is a very important part for the thermodynamics. So here again, we come back and then we have seen that the temperature is not constant with height in the atmosphere. It decreases with height in the lower parts called troposphere. Again, above troposphere, the temperature increases with height in the layer called stratosphere. Above that, it decreases again, mesosphere, thermosphere, and again in the mesosphere, the temperature increases, etc. So for the weather, most importantly, we are bothered about what is happening in the what is happening in the troposphere, that is the lower part of the atmosphere where the temperature decreases with height. That's what we have seen. And so we spent some time on that particular property called lapse rate. Lapse rate is the rate at which the temperatures decreases with height. So lapse rate is the rate. So as I said, though I mentioned 6 degrees centigrade is the lapse rate, is the rate at which the temperature. There's an average value, but it is over the space and time. So there is a large variability in this rate of temperature. But we should know how and why the lapse rate changes. So the lapse rate is dependent on the temperature, pressure, and the degree of saturation. Saturation means it is a property of the water vapor. That means any particular small volume element of the atmosphere, how much of the water vapor it can withhold, it is dependent on the temperature and pressure. We will see a little later, but at this particular time, you please kindly accept that the lapse rate is dependent on the temperature, pressure, and the degree of saturation. I will explain to you that saturation also. If we see that, here is an important concept. Time and again, we will be using this. In the troposphere, atmospheric pressure decreases with height. So as the altitude increases, or as we go up from the surface above into the atmosphere, we know that the atmospheric pressure decreases because we have seen the atmospheric pressure is the weight of the air column above it. So as you go up, the weight of the air column would decrease. And so the pressure decreases with height. There's no doubt about that. And if you consider an air parcel, I will also come and explain to you what this air parcel is. Therefore, if you have a small volume element of the air called a parcel, if it is rising, if it is taken from one particular height to a higher height, then what happens is the parcel or that volume element of air is subjected to lower pressure. So because of that reason, it expands and it cools. So basically, if air is taken up for some reason, don't worry about the reason at this particular instance, but if the air is taken from one level to a higher altitude, then what happens is it is subjected to a decreasing pressure or lower pressure around, and so the parcel expands. That means the volume increases, and so it cools. So apart, there are two things that work on the air parcel. So there is a heat that is coming from the ground below, as we said before, and the parcel has a tendency to cool. So in general, the temperature decreases with height. Okay. So the main reason for the temperature to decrease with height is the parcel being supposed to lesser pressure around, which means that expansion and cooling. Here we need to, because I mentioned air parcel here in meteorology, we use the concept of air parcel. It is very important. That means what is this air parcel in a because the atmosphere is a continuous medium. It is a mixture of gases, and then there is no breaks in the atmosphere as such. And how can you say or see or envision a parcel of air different from the rest of the environment? So we introduce the concept of an air parcel, which is important to understand the characteristics, and you will see its usage as we move forward. So we imagine a small volume element of air with independent characteristics of temperature and humidity different from the surrounding air. That means so you see that this is it could be having the same temperature and humidity to the surroundings, but it also could have a different temperature and humidity at some particular instance. This is true in the atmosphere, because if there were not to be separate entities, we will not be able to explain the observations of different weather phenomena such as thunderstorms, rainfall occurrence only over a small area and only over some small regions. So the weather different from location to location, and we see how only a particular location or a small area is subjected to some particular kind of weather phenomena such as rain formation, rain occurrence can be explained only the concept of an air parcel. And so please, if you have any doubts, I can explain much more at the end if you still have. But the concept of air parcel as which has the characteristics independent of itself. That means if you are moving the air parcel from one level to another level, the air parcel will be subjected to only the changes in the pressure, but it will not interact, or it will not be contaminated or mixed with the surrounding air. That also I will say that. I am going to introduce another concept called adiabatic. So we also use a process called adiabatic process, which is very, very important to understand the thermodynamics of the atmosphere. An adiabatic process is a thermodynamics process in which there is no exchange of heat between the parcel and its surrounding atmosphere. So first we defined a parcel, which is a small volume element of air, which is independent of its characteristics with the surrounding environment. Now we are saying another process. That means we are defining a process wherein the parcel and its environment will not have any exchange of heat. That means the particle will be able to keep its entity in terms of its properties, in terms of its temperature and the water vapor molecules. That is very important. This means that heat is adiabatic process means heat is not exchanged neither during expansion, whether it is if it is ascending, because of the low pressures, the air parcel would expand, or if the parcel is brought from a higher height to a lower height, it would be subject to higher pressure, and so it will be subject to compression during these two processes. And heat is not exchanged between the volume element of the air. Consider that mean an air parcel would is assumed to be in the atmosphere at one particular location. If its movement in the atmosphere upwards and downwards is considered to be adiabatic, that means it will not have any exchange of heat with its surrounding environment, whether it is a reversible or irreversible process. So we see the lapse rates in different states of the atmosphere. We have to understand now that we have the environment lapse rate. Normally, please remember, this is environment lapse rate is the one which is observed taking measurements at different altitudes, and you plot the temperature with height. That would determine the environmental lapse rate, at that particular location at that particular time. So the environmental lapse rate is a particular quantity that is derived as a representative of the environment at a particular location at a particular time. So the environmental lapse rate is clearly depends on the location and at the time of the observation. Well, there is another definition called standard lapse rate. Standard lapse rate means you take the observations of the temperature with height over lots of time periods, and then you average. Then for that particular location, you can say this is a standard. That means an average lapse rate that taken as an average from several of the environmental lapse rates that data is being collected over a long time period. Then you can obtain the standard lapse rate. Well, apart from this, there is one important first one, because in the said dry adiabatic lapse rate. So here we assume the atmosphere and the parcel, especially the parcel, is purely dry. That means there is no water vapor inside the parcel we consider. So the rate at which the temperature decreases in that parcel of dry air again, dry air means there is no water vapor present in that volume element of air or in the parcel. So the dry adiabatic lapse rate is defined as the rate at which the temperature of a parcel of dry air decreases with height as the parcel is lifted from a height to different heights, considering a reversible adiabatic process. So reversible means adiabatic process means it is the heat is not exchanged between the parcel and the environment, and as the parcel goes up, it is subjected to expansion, lower pressure around, and so it is cooling. And the same parcel, if it is brought down to the lower level, that means from a higher altitude to a lower altitude, it is subjected to higher pressure and so compression, and it will warm again. So it is a reversible adiabatic process. That's what we mean by reversible. So the dry adiabatic rate is 9.8 degrees centigrade per kilometer. The dry adiabatic lapse rate is a constant. I am making some statements. You can ask me how I'm going to make a derivation to show how to obtain this dry adiabatic lapse rate. But at this time, first I will give the information to you basic. Then I will also give you how you get it. So this dry adiabatic lapse rate is G by CPD. G is acceleration due to gravity. CPD is the specific heat of dry air at constant pressure. So that specific heat constant, you know. So the dry adiabatic lapse rate is G by CPD essentially. So we have seen under purely, if the parcel is purely dry, no water vapor at all. And the water, then we come to moist. That means some water vapor is present, but it is not saturated. That means I think all of you have an idea about the property of saturation. If every volume element could be seen, consider its temperature, it will have, suppose it has certain water vapor molecules. If the ability to the ability of the air parcel to hold the number of water vapor molecules is dependent on the temperature and the pressure, keeping the pressure constant, because only at that particular pressure level, pressure being constant, it is purely dependent on the temperature alone. And so if the temperature, a parcel has a certain temperature and certain volume, number of water vapor molecules. So if you cool this parcel, if the temperature decreases at some particular temperature, the number of water vapor molecules that can be held by the parcel is equal to the number of molecules, then we say that it is saturation. That means at the saturation point, the number of the water vapor molecule that are present in the volume element of the air or the air parcel are just enough. And any more of the water vapor addition or any more of the decrease, it cannot hold the present water vapor molecule. So each volume element has a point of saturation, which is dependent on its temperature. If necessary, please ask me. I will put a question. I will explain to you again. The adiabatic lapse rate of an unsaturated, that means some moisture is present, but it is not enough for the saturation. In that particular instance, the lapse rate is being given, still shown as tau d. It is the dry adiabatic lapse rate only by, it is equal to G by 1 minus Q. Q is the specific humidity. So you know the specific humidity of the parcel. Probably, I presume you know how the humidity is in a volume element of air is expressed. So what is the humidity mixing ratio? What is specific humidity? What is the absolute humidity? What is relative humidity? Please, I suppose you know. If you have no idea, I will show them in the next class, at the beginning of the next class. So where Q is the specific humidity, please, it is a measure. It is a measure. The specific humidity is a measure of the amount of water vapor present in an atmosphere. It is actually the mass of the water vapor by the mass of the dry air. It is specific humidity, mass of water vapor by mass of dry air. So CPV is the specific heat for the water vapor, specific heat for the dry air. And so we have, it can be written G by CP. CPD is now split up one particular part. 1 minus Q means that particular amount of mass, which is not the water vapor. For water vapor, you have certain molecules. So Q into that particular Q is given by, as I said, it is the mass of the water vapor molecules by the mass of the dry air. And so Q into CPV. The remaining part is dry molecules. So you have CPD. So we can write the tau d is equal to G by CPD, previously shown for the dry adiabatic lapse rate. Very easily, it can be split up. The denominator can be split up. One particular term that concerns with the water vapor part and the other part concerns the dry part. So it can be written very easily. I have given you the values of the CPD, which is 1004 joules per kilogram per degree Kelvin. Say for water vapor, it is 1865 joules per kilogram per degree Kelvin. So the specific heat of the specific heat capacity of the moist air is slightly higher than the dry air, but it is still less than about 1%. So the dry adiabatic lapse rate of the moist unsaturated air is slightly lower because now we are adding something here, 1865. For the Q part, you are adding 1865. For the remaining part, you are multiplying with only 1004. So the denominator is slightly higher. So you will have a lesser lapse rate value. So the moist unsaturated air will have a lapse rate slightly lower than the pure dry adiabatic lapse rate. Okay. But however, most of the times we ignore this small difference. But you should know what difference it makes for the pure dry air, moist, unsaturated air. And we come to moist adiabatic lapse rate. That means the air parcel is completely saturated, and whatever the water vapor molecules that are present are enough at that particular temperature to satisfy the saturation criteria. In that particular state of the atmosphere, and what is the rate at which the temperature decreases in that particular one, as we see that now it is now it should be much lower than the moist unsaturated. Why? Because the saturated air parcels cool more slowly than the unsaturated parcel because please remember, as we said, as the parcel, the dry dry air would rise and it would expand and cool. Whereas if a saturated air parcel is raised from at the beginning, it is saturated. So if it is lifted up further, what happens is the temperature further cools as of before, but there is certain amount of water vapor because the parcel cannot hold the water vapor is beyond saturation. So certain number of water vapor molecules will be subjected to condensation. And when the process of condensation takes place, that is the phase change from water vapor to liquid, latent heat is released. Latent heat is released. So the inside the parcel, as the water vapor is converted to liquid water due to the process of condensation, heat is released. Though the air parcel is subjected to cooling because of the pressure expansion, lower pressure outward and then the expansion, cooling takes place. But the latent heat release will to some extent augment that cooling, so the parcel is slightly warmer than it would otherwise be. So the mathematical expression I have written straight away. Don't worry about this formula. Here also we see that there is a G acceleration CPD, and here there's some terms come, and because of the saturation mixing ratio, because of the saturation mixing ratio, we see these extra terms that is coming in. Certainly, I will make a derivation for the moist adiabatic lapse rate and the adiabatic lapse rate from the fundamentals after I make a definition of some important other fundamental variables. Okay, so this is take it for granted at this particular time. So the formula for the moist adiabatic lapse rate is given by this, and as we see here, and as I explained, you will see that the moist adiabatic lapse rate is smaller than the dry adiabatic lapse rate. Okay, that's what I think we have. I do not know how much time I have. Can I go further? Dr. Lakshmi Kumar?
Sorry, it's already time up. Maybe you can take 2 to 3 minutes.
Oh.
Or you can continue next lecture, sir.
Yeah, that's what I'm thinking. If you think it is,
I see there are
because I will be teaching again the same things.
Yes.
If you feel that, because at this time I can stop it, because I have taken some time in explaining the previous things. I can postpone the explanation of these things to the next one. And if I get a feedback of how the content is, if it is too elementary, I can go and cover a bit faster. Or if the participants feel that it is important for all the information to be given, even though I take a little more longer time, I will try to do so. Okay. So for today, I will stop here. Okay.
Thank you very much.
Thank you.
Thank you very much for your.
I will be happy.
Excellent presentation. And I think there are so many question and answers from the participants. I think many are praising you a lot in their comments. So now I request Dr. Akhilesh and Dr. Madan, moderators of the question and answer session, to handle the session. Over to you, both of you. Dr. Akhilesh, you can start.
All right. First, am I audible?
Yes.
Yeah. Okay. So the first question is coming from, it's an anonymous question. I think the user has not been properly registered properly. What is the concentration of water vapor in terms of per centimeter cube? So
in terms of,
I don't know that it's a general question. Probably he's not specifying where exactly. Yeah, what is the concentration of water vapor in terms of centimeter cube, per centimeter cube? An area of maybe a volume of.
He wants the density.
Yeah, I think so. The water vapor
density. The density I have given.
Yeah.
It is given on the one of the first few slides.
Okay, and then the next question is from Tamda Jayasri and Sushil Kumar.
Given the density
I think, sir, these questions are put in order of their appearance. Later on some slides, you have answered many questions. So I would simply say that these questions are already there in the slides. If they go back to the recorded presentation, they will find.
Okay.
Okay, so we'll move to the next question, which is probably much more general. So Shil Kumar and Tamata Jaisri has asked, what is the main difference between aerosols and particulate matter?
Particulate matter contains many other things. Pollutants only one part. Pollutants,
I hope
there are many things. Pollutants are many kinds, and actually, here we don't concentrate on what is a pollutant, but whatever the pollutants that are released into the atmosphere, depending on their size, they are considered as particulate matter of some size, like below 2.5 or between 2.5 and 10, like that. So there are many kinds of particulate, the aerosol that are being released, and then they are being graded as particulate matter depending on their size.
Right, I hope
so. Another question from Pramod Kumar. He asked, in modern days, huge nitrogen fertilizer used in agriculture. Is nitrogen indirectly support greenhouse gas?
To some extent. I did not give, there is a lot of chemistry in between. Definitely, if you use more of that, it helps to formation of nitrous oxide. And when the nitrous oxide forms, it definitely works as a greenhouse gas. That's the reason why during the last 250 years, there's a gradual rise in the presence of the nitrous oxide.
Another question from Rajendra Kumar Panda. He asked about, can decrease in atmospheric pressure and density affect gravity of Earth in any way?
No, again?
He asked about, can decrease in atmospheric pressure and density affect gravity of the Earth in any way?
No way. It is absolutely different. See, the mass of the Earth is so huge. The mass of the Earth is so huge, and it pulls all the things towards its center, because the gravitational force is depending upon the mass of the element which is having this force, which is executing this force. So the atmosphere molecules are attracted because of the gravitational force pulling it towards its center, and any amount of difference in the density of the atmosphere affect the gravitational force. No.
Okay, next question from Pramod Kumar. He asked about, can we say that ozone content in lower stratosphere, or concentration of ozone more in lower stratosphere?
Ozone content in the lower stratosphere.
Yeah.
Yes. So the question is what, please?
Concentration of ozone more in lower stratosphere or not? His question is that.
Yeah, actually it is more in the lower stratosphere, and it is also spread in the other parts of the stratosphere to some extent. It is also present in the troposphere to some extent. Even near the ground, we find some ozone. And in the upper troposphere also, we find some ozone. Near the surface, we call it also as a pollutant. And when it is there in the upper troposphere, it is also considered as a greenhouse gas.
Another general question from SAA. He asked about how the correlation between aerosol and rainfall, he said.
No, I think that question does not pertain to my lecture. It is altogether a different kind, because there is a lot of physics between that. Somebody, when it goes to the cloud physics, he would explain how the aerosols, some particular kind of aerosols would help the formation of the clouds, like condensation nuclei. Not all of the aerosols would be helpful or would act as condensation nuclei. So some of them would act and enhance. Some of them actually may inhibit the formation of the clouds because too much of condensation, too much of the condensation nuclei also. So some particular kind of a mechanism that works between aerosols and rainfall. But I mentioned the presence of aerosols only as a composition of the atmosphere, but the physics of the physical relation between that is more would be explained, I think, in the cloud physics.
Okay, Dr. Akhilesh, do you find any
Yeah,
more
absolutely.
questions?
I think many questions. Yeah, thank you, Dr. Madan. I think many questions are related to, beyond the topics here. So, but one question I think somebody asked that is it mean aerosol is parameter provided by satellite and PM from the ground station? So that's again is more in the the aerosol
not
side.
for this lecture.
Yeah, exactly. That's what I'm saying. Several questions are like that. But somebody named Arun Kumar has put some questions related to some doubts. He said why there is a constant temperature in tropopause and stratopause. Did the molecule in the layer is inactive to radiation? Why there is a constant temperature in tropopause, and stratopause?
No, lower part of the stratosphere, there is a small layer, and that is because of the presence of the ozone, concentrated presence of the ozone in the lower stratosphere, and the absorption of the ultraviolet radiation, that particular makes it a little isothermal. Then again, the temperature would increase, because at higher levels, again, the concentration would be different, and then absorption capacity would be different. So I think maybe I cannot answer beyond that.
Yes, sir. I think to add one or two more quickly from the same user, Mr. Arun Kumar, is asking what will happen to the energy absorbed by ozone in stratosphere. Will it convert only as kinetic energy or in some other form of the energy?
That's not our question. No.
Yeah, and the last one, I think that is much more relevant. He's asking is it technically possible to have an air parcel with adiabatic properties in our atmosphere? Is an ideal condition. Ideally,
yeah, that is as I said, an absolutely envisioned air parcel, completely sealed from the environment, is not physically possible. Is not physically possible in the atmosphere, but the process we are assuming, like the exchange of heat between the earth and the particle keeping its own properties without getting sufficiently mixed by the environment, is very much possible and is observed. Otherwise, we will not be able to explain many of these phenomena.
I think many questions you have already answered, sir, and some of the questions people have asked, which are already answered in your slides. Probably, if they can go back to presentation,
yes.
recorded presentation,
or anything, maybe they can send me, and
they can email or communicate. If
Yes.
there is any question, Dr. Madan, if you have noted, please go ahead. Otherwise, we will go to the next part of the presentation. Then.
Akhilesh,
I think almost the
question
question are answered. Yeah.
Akhilesh,
Yes.
there is one
Right now.
question which has got to my mobile from one of the participants. What is the reason for the presence of tropopause, stratopause, and other immediate layers? And why is the temperature constant, not changing here?
Yeah, I think that I already put, I think.
See,
But yes, please.
see, our lecture actually is not on the vertical structure of the atmosphere alone. I had to show all of them because we need to explain how the temperatures behave in the troposphere and how the temperatures would change, the structure would change in the stratosphere suddenly. But there is a lot of physics that is happening to explain the temperature structure in the upper stratosphere, then the thermosphere, mesosphere, thermosphere, etc., exosphere. So I think they should go to see the better physics. I think we are confining ourselves only to meteorology, weather-related things, and my lecture is mostly confined only to the troposphere and a little part of the stratosphere.
Before ending, Dr. S.N. Misra has one question. What proportion used for ice and salt for their Kelvin scale, and the total mass in a troposphere is 75% or it contains 99%?
Actually, that's actually a history. You should go to the original experiment, how Fahrenheit when I was reading that I was very curious how Fahrenheit derived these things very much different. Actually, all the three, how they came up, I was very curious. So he started with ice and salt mixture, and honestly, I'm not aware how much mixture, and then how he experimented to reach the freezing point, boiling point of water from that mixture.
I guess
But
that's
I
all
thought
for
that information the participants should know why there are three different scales and how they are different from each other, and why so three things have come up into the science. At least that's what I thought I should mention.
Absolutely, sir. Correct. So I think many questions have already been answered. Lots of questions, so many thanks, so many, applause, praise for your lecture. I think it will continue. I think hundreds of messages have been received in question answer session. Many other, probably we will not be able to cover all the questions because many are
I want to
beyond
know
the
from the
topic of
participants, Akhilesh.
Yeah.
I want
Yes,
to
sir.
know from the participants if they think it is too elementary and I'm spending too much time on
Yeah.
the elementary things. I can go a bit faster. Otherwise, if they think that this particular kind of thing is important, because as a teacher, I do not take anything for the student to go and refer back. That's why I try to give all the information that's necessary to understand my lecture, and try to make it as simpler as possible. But
Sure.
if the advisory panel as well as the participants feel that I should not go into so many fundamentals details, I could skip.
I think, sir, I think we will certainly ask Dr. Lakshmi Kumar to collect this survey.
Yeah,
But
maybe.
these lectures are for basics only, and Dr. Somesh wants to say something to add, I think, further.
Sir, can I 1 minute say? There are three immediate comments for this question. Thanks for the interesting lecture. This is the best way, sir. Elementary information is required.
Okay.
Yeah, actually, I would like to say that when we designed this lecture module, we thought in mind that this is supposed to be for the beginners who have no background in meteorology, or they are somehow working in some aspects of climate change, etc., but without having any knowledge of the atmospheric science.
I remember.
So this entire lecture is supposed to be designed for that. And actually, if you really want to learn atmospheric physics, then it is a full semester course. And the entire atmospheric physics is taught in 45 lectures. You can just imagine, a 3 credit course in one full semester. Whereas we have just tried to focus on some of the important topics like atmospheric thermodynamics, which also is a very elaborate subject, and atmospheric radiation and cloud physics, all in four lectures only. So just you can imagine how much squeezing we have tried to do for the entire atmospheric physics course. Nevertheless, if you really want to learn about the atmospheric physics, we can certainly provide you some of the references for the textbooks which are taught in the MSc level, and you can definitely go through those textbooks to learn more about the atmospheric physics. So that is what is my thing to say. Dr. Lakshmi Kumar, yeah.
So, Dr. Someshwar Das, do you think I should continue the same way as I did now?
Yeah, I think so, sir. Yeah.
You can inform me later.
Yeah, that's fine. In my opinion, because we have already mentioned many times that this course is for the beginners. But if somebody is attending this course, who are already having a PhD degree, but I don't know PhD degree in which subject, whether in atmospheric science or other subject. So if somebody is attending the course with a PhD degree, then he should understand that he or she should understand that this is for the beginners, and we are trying to teach from the very beginning level. Therefore, I think we should continue the same standard. And I think the lecture was really, really very good. For that matter, started from the very beginning how the atmospheric structure looks like, the stability, atmospheric stability, etc. So I think we should continue the same way.
Okay, thank you.
Yeah.
Thank you so much.
Right. Thank you.
Can I stop sharing the screen?
Yes, sir. Yes. So I see some of the comments from the participants. They are asking, I think they are mentioning this is the way they want actually. Okay.
Yeah.
Yes.
Yeah, I answered some of the questions in the chat box, in the question
Yes,
and answer box. I answered some questions. And
Yeah,
also,
Cloudburst.
yeah, Cloudburst, and all people are asking same question in YouTube channel
Correct.
also, and also in the question and answer box, etc. So, and some of them have asked whether lecture slides will be provided. Yes, we have been providing the lecture slides, and also we are planning that at the end of the lectures, all the lectures, we shall try to make an abstract book, about 1 or 2 pages abstract of each lecture, and then share with all the participants.
I think
So,
most importantly, sir, these all recordings will be available on
yes,
YouTube channel.
yes,
So
exactly.
going through the lecture, I think recording would be much better, right? Much better.
Right,
I
right,
guess.
right. We can always go through that.
What about the time constraint? Do you think I have taken more time?
We
you
started
can-
actually, a lecture
can-
started at
Yeah, it's a bit late.
3:25.
For 3:30 it started.
3:25, 3:30 it
I think at
started.
least
So
1.5 hours it should be.
about
You
1.5 hour
can,
lecture.
you can restrict 60 minutes are your lecture, 60 minutes.
No. So
No, unless there is some other constraint,
Yes.
you see, unless there is some other constraint, it is, for me, it is better to give as much information as possible. You see, instead of not cutting off some information, unless you think I can easily cut off certain derivations which I come back. This is mostly descriptive, but now tomorrow, next class, I want to show the derivation for potential temperature, dry adiabatic lapse rate, moist adiabatic lapse rate, how the expressions were derived, then probably, so as you wish.
Yeah. Okay. Okay.
Can I,
Yes,
is
sir.
it closed now?
Yes, fine,
We
sir.
can have a photo session. I think photo session.
Yeah. Thank you, sir, very much for your excellent presentation. So we all have enjoyed it. I am also sure that all the participants have enjoyed it. So we would like to hear our next lecture also. Thank you very much. Before I think closing the session, I request Dr. Mohan to provide the vote of thanks.
Yeah, let us have a photo session. Let everybody switch on the video.
Switched on video.
Yeah, please turn on your video, panelist. Madan, you are taking or I'm taking?
Mohan is taking, I think.
Just a minute. Taken.
Yes. Mohan. Proceed.
Yes. Okay, just a minute.
Okay, thank you.
Good afternoon, everyone. I believe it is a great honor and privilege for me to present the vote of thanks for today's International Lecture Series session. So on behalf of the participants of SAMA, I'm glad to be here to express my vote of thanks in this session. First and foremost, I would like to heartily thank our today's resource person, Dr. D.V. Bhaskar Rao sir, Honorary Professor, Department of Meteorology and Oceanography, Andhra University, India, for being here with us and for his excellent delivery. I was listening to your speech with keen interest, and I believe all other participants did the same and enjoyed it most. I'm confident and hopeful enough that your sharing of knowledge, experience, and views with us on atmospheric physics, especially atmospheric thermodynamics, this is lecture 1, gave us a new idea for thinking and challenges and would encourage us to work in this sector in future. Our heartfelt gratitude goes to the respected members of the Coordination Committee of SAMA training course, especially warm thanks to AVM retired Professor Dr. Aditya Agi sir, he is the president of SAMA, Professor Dr. Someshwar Das sir, he is the secretary of SAMA, Dr. Gao Mo Wu, Director General of Department of Meteorology and Hydrology, Myanmar, Dr. T.V. Lakshmi Kumar, SRM IST, and he is the session moderator of this lecture series, Dr. Rohini Bhawar, SPPU, India, Dr. Madan Sigdal from Tribhuvan University, Nepal, Dr. Akhilesh Mishra from National Center for Medium Range Weather Forecast from India, Dr. Swagata Paira from BIT Mishra, India. and Board of Directors and the organizing committee for arranging such an effective and excellent training program. I believe this program has become a fruitful and supportive one in changing the knowledge, skills, and attitude of the participants to a better level. Finally, I would like to thank the members of SAMA and all other participants from SAMA countries and abroad for their spontaneous interaction, for making the program live, enjoyable, and memorable. Thank you all once again for being here with us. Thank you all.
Thank you, Dr.
Thank you very
Mohan,
much.
and
Thank
thank you all participants for joining today's lecture. So next week on Saturday, at the same time, we will be meeting. The next lecture will be mainly on the pressure distribution. So this lecture we have seen the temperature. Now next lecture mostly will be pressure distribution will be covered. So the tentative topics will be covered under pressure lecture is atmospheric stability, hydrostatic equation, and partial pressure altitude relationships. So I request all the participants to attend the next lecture without fail. So we'll be sending a lecture of PowerPoint of the lecture in a couple of days. So thank you very much, and I thank you all for joining. Thank you very much. Thank you.
Thank you all. Thank you.
Have any clarifications required, you can write an email to SAMA so that those questions will be taken to the Spanish or the expert member. Thank you. Thank you very much.
Thank you.
Thank you.
Can we stop live streaming?